Hello everyone. I hope you are all having a great day. Today, I will be presenting our research towards infusing auxiliary knowledge for distracted driver detection. In this presentation, we'll explore the importance of addressing distracted driving, the innovative methods that we tried out, and the results we achieved. Before that, I want you all to watch a quick video put out by the National Highway Traffic Security Administration.
Distracted driving is dangerous, but some people just can't seem to help themselves. There's the steering wheel propper, the sneak-a-peeker, the fast scroller, the nightlighter. And it's not long until they become the fender benderer, the got-a-ticketer, the veering off the road, the driver who kills someone. Enough with the phones already. Just put them down.
Right. So in 2022 alone, there were about 3,308 people killed and nearly 290,000 people injured in traffic crashes involving distracted drivers. That's a lot. While the video you just saw talked only about using phones, distracted driving actually comes in many forms, be it drinking, eating, adjusting control panel, reaching behind, yawning, singing, etc. So, when you're behind the wheel, your sole focus should be on driving safely. Anytime you divert your attention from the road, you're distracted driving. And that is the definition of distracted driving that we'll be following throughout the presentation. Yeah. Yeah. So distracted driving has become like a major threat on roads, putting not just the driver at risk, but also the passengers, pedestrians, and everyone else on the road, making it like really necessary to address these issues. Yeah, therefore, in literature, distracted driving detection problem has been formulated as detecting and classifying various distractions, such as texting, eating, from in-vehicle camera feeds. The task is challenging because we need robust models that can generalize to a diverse set of driver behaviors without requiring extensive annotated data. Traditional methods have relied on various end-to-end learning and computer vision techniques, but recent advancements in knowledge infusion and neurosymbolic AI present new opportunities for improving scene and context understanding. So, we claim that there is a valuable auxiliary knowledge that can be either computed or derived from visual inputs alone. Specifically, we hypothesize that by infusing such knowledge with current computer vision models, we would improve the overall detection capabilities and robustness while not requiring the heavy computation demands of ultra-high parameter models. To this end, we propose KID3, which is short for Knowledge Infusion for Distracted Driver Detection, which is a novel, simplistic method for distracted driver detection that infuses auxiliary knowledge about inherent semantic relations between entities in a scene and the structural configurations of the driver's pose with visual cues. Like our approach constructs a unified framework that integrates scene graph, driver pose information, and visual cues in a video frame, creating a holistic representation of driver actions. And we did this experiment on a real world open data set, and KID3 achieved 13.64% accuracy improvement over the vision-only baseline, demonstrating the effectiveness of such an integration. Yeah, so let's talk about the data set we worked on. Uh, Real-world data sets for distracted driver identification typically include annotated video sequences from camera mounted inside the vehicle. We selected SynDD1 to be used for experiments due to higher number of distracted behavior classes and the diversity, including variation in like lighting conditions, driver appearances, and the use of objects and people in the background, etc. So SynDDV1 had 60 videos, 30 in training set and 30 in test set. The data set consists of images collected using three in-vehicle camera positioned at uh, one on the dashboard, one near the rear view mirror, and one on top right window corner. The video sequences are sampled at 30 frames per second and are manually synchronized for the three camera views. And yeah, each video is approximately 10 minutes long and contains all the 18 distracted activities. Yeah, so here are the 18 predefined classes in the dataset. Only one class being normal driving and everything else is distracted driving. Right. So let's talk about the proposed solution. We constructed a single ML pipeline to combine the latent encoding of the three modules, uh, image encoder, scene graph generator, and pose estimator. Each of them take an image as an input, process it, and give out a meaningful vector representation. We then concatenate these representations using a feed-forward MLP to classify the input image. And each of them, in turn, try infusing visual cues, semantic relations, and the driver's pose into the model. Yeah, so pre-processing, the first step in our pre-processing is the image encoding. So we used VGG16 to obtain robust image embeddings that effectively capture the visual features. Next, for the scene graph generation, we used the realtor model to generate scene graph that structurally represent the relationship between various objects in an image and capture high-level contextual and semantic information, allowing us to explicitly inject knowledge into our detection pipeline. To generate scene graph, uh, we used realtor and then that was followed by a graph convolutional network to create node representation. We then take the mean of these node embeddings from the graph level representation, and this is used as the graph encoding. Yeah, and then we also use like a state-of-the-art 2D pose estimator, OpenPose, to extract key point coordinates representing various body parts. These coordinates are normalized uh, and structured to consistently represent driver's pose. Additionally, we included features like hand to eye distance, angle, neck angle, hand object distance, uh, which are derived to enhance the model's ability to accurately classify the driver activities. Yeah, so let's talk about our first experiment. Uh, in the first experiment, we used existing CV models to establish a baseline performance for the frame classification task. We fine-tuned the VGG16 model to assess the performance of traditional CVM models. To achieve this, we froze the weights of the entire model and unfroze only the classification layers. So in the diagram that you're seeing, everything else here is frozen, and only these few classification layers are unfrozen. And the sixth classification layer, which was a linear layer that went from 4096 to 1000, was replaced with a linear layer that went from dimension 4096 to 18 to match the number of activity classes. This modified model, we just fine-tuned it on our classification task, allowing these classification layers to adapt to the specific features of our data set. Yeah. And in the second experiment, uh, we retained the VGG16 model used earlier. However, we discarded the last two classification layers. Like the base model was used with the first four classification layers. This was because number one, the last layer would have given us an 18 sized, a vector sized 18 of 18 dimension, but we wanted something like 4096 dimensional image embedding. So we just discard the last two layers. Moreover, the earlier layers in the network capture more general visual features, so making them like particularly suitable for transfer learning applications. Yeah. So then we combine the image embedding extracted from VGG16 with the scene graph embedding that we got after running the GCN on the generated scene graph using the scene graph generator. So the GCN embeddings are then concatenated with the image embeddings to create a unified representation. And then linear layers were used to integrate these information streams, resulting in the combined model. So basically, the unified representation is then passed to a bunch of linear layers that do the combination part. And yeah, uh, coming to experiment three, to further improve the scene representation and enhance the model's understanding of driver activities, we incorporated pose information. So pose information includes location of objects using bounding boxes and outline of human skeleton with key coordinates like eyes, nose, face, etc. So we obtain bounding boxes from the realtor itself, but we also used models like YOLO to get all the bounding boxes. And then we added engineered features based on external knowledge, such as the distance between hand and face, or hand and and phone or bottle if detected using YOLO. These additional features were integrated with the existing image embeddings and scene graph embeddings. The classification model was then retrained on these enriched features to provide a more comprehensive understanding of driver activities. Uh, yeah. Let's talk about the results. We assess the model's performance using two metrics mainly, accuracy and F1 score. The vision-only model from the first experiment achieved an accuracy of 79.64 and a F1 score of 0.81. By incorporating scene graphs, we observed a significant improvement with accuracy, followed by 11.8% and F1 score by 9.88%. The best performance was achieved in the complete model, which included both scene graph embeddings and the pose information, reaching an accuracy of 90.5% and F1 score of 0.91. So our findings confirm the initial hypothesis that incorporating additional knowledge with visual features would enhance the performance of the distracted driver detection task. The evaluation study further uh, shows the contribution of each type of auxiliary knowledge. In this case, scene graphs were found to be the most valuable, and emphasizing the importance of explicitly representing semantic information and integrating it with visual features. Yeah, so here are the F1 scores and support for individual activities, that is classes, across the three methods. So here we observe that our method was particularly effective in identifying certain classes such as eating, adjusting control panel, singing, etc. So we interpret this as evidence that our approach successfully interpreted auxiliary knowledge, enhancing our model's performance for these particular classes. Uh, Limitations. So our drawback of our approach is the dependence on annotated data for training. While we used a combination of supervised and unsupervised learning methods to fix this issue, the availability of labeled data continues to be a primary limitation. Additionally, our method may face difficulties in complex and diverse driving situations where the relationships between objects and actions are less clear-cut. Finally, we did not investigate the use of foundation models like vision language models in our experiment. Like our primary focus in this research was to evaluate the impact of infusing auxiliary knowledge on distracted driver detection tasks without relying on complex, large parametered computer vision models. And yeah, so like to conclude our work, we presented a novel and efficient method for for detecting distracted drivers that utilized auxiliary knowledge extracted from visual inputs. We demonstrated the effectiveness of this approach in improving detection accuracy without relying on computationally intensive models. And yeah, this research has potential to significantly contribute to the development of reliable and scalable solutions that improve road safety. Future research will address the limitations I just discussed in the previous slide. Furthermore, we intend to explore the integration of other knowledge representations like temporal graphs to further improve the performance of distracted driver detection systems. Additionally, we plan to investigate the role of language models in this task. Yeah, so here both our code and the data are publicly available. Feel free to visit them. And yeah, thank you for your attention. I will now open the floor for any questions that you might have. And yeah, thank you. Thanks a lot.